Cool. Hi, everyone. I'm James. I have a love-hate relationship with distributed systems. And I've devoted my whole life to distributed systems. I used to work in cellular and satellite and Wi-Fi protocols, and then I did a PhD in consensus protocols and distributed transaction commit, and then at Dropbox, designed the multi-exabyte distributed storage system and the distributed database that runs several million consistent transactions per second and multi-homing, all that kind of stuff. Worked closely with Jamie, who designed the sync protocol at Dropbox. So I guess I chose this life, but distributed systems are frustrating. And if you don't think distributed systems are frustrating, I challenge whether you work in distributed systems because they are hard. They have very subtle, difficult, emergent properties that don't show up until way later on. And I'm going to drop some hot takes here that I stand behind strongly, right? I don't have no desire to gatekeep. I want more distributed systems engineers. And if you want to be one, please come work at Convex. But talent is plummeting in this area. There is just not a lot of deep distributed systems people on the job market. Everyone's thinking about building AI or building applications. I think that's great, mostly. People are focused on building value, products that have value. And I don't think the robots are coming to save us, at least for a while, right? And again, if you think the LLMs are good at systems architecture, I just don't think you understand systems architecture yet, right? Because there's good reasons why LLMs are not good at this, right? Because a good distributed system is not one that just works. It's one that's simple and maintains that simplicity and that maintainability over a course of years as your requirements change, as your workloads change, and as it grows over time. I can't point you at a good training set for distributed systems. I can't give you a good eval for distributed systems. And building good distributed systems means reasoning about unrelated components and how they interact in ways that don't mesh well with context windows, right? So I think there is this looming systems crisis, largely for a good reason. People want to build applications, but they don't want to build like databases and sync protocols and all that kind of stuff. Great, someone has to solve that problem. That's why we're all here, right? Now, I'm going to go down my personal tangent of how I think systems should be designed, right? And I think the industry has trended away from the architecture that I tend to like. And I think in two ways. We've given up on transactions. I'll talk more about this. I think transactions are the most valuable building block for like concurrent systems. And we have this amazing, wonderful thing called client-side reactivity. We have React. Isn't it cool that we just think it's normal now that data changes on your client and your UI just re-renders consistently? You don't have to do that manually. But there's no relationship to the back-end state, right? So we have client-side React. We've made the easy problems, or like at least the user-facing tractable problems, very simple, and we've made the back-end problems even harder, right? So I think in many respects, we've created maximal race conditions, right? We've taken away consistency. We've added all this power. We haven't tied that to the data that lives on the server, the important stuff. So in my mind, the holy grail of full-stack development, the primitive that developers need, the modern application developer needs, is automatic end-to-end consistency from the server to the client. And this is what I'm calling sync. We're going to have a panel session later on. There's lots of definitions of sync, right? But this is my version of sync. Certainly doesn't preclude other definitions of this. But I think, to me, sync means keeping data on your client in sync with the data on the server. This is an example of what this looks like. In Convex, this is just me messing with state in the dashboard on Convex, and this is a little demo app on a cell phone. This is just going over the internet, and it's happening instantaneously. And when you update state on the server, the client updates in a consistent way. I'm not talking about local first. I think there's a lot of really interesting local first ideas out there. We haven't quite nailed it yet. We have 2 working prototypes of local first in Convex with full offline support and everything. Just haven't quite nailed it yet. I'm going to focus on what platforms need to look like, what the building blocks need to look like to make race conditions go away. So I think this is the operating system for application development. I think this is the 3 things, my candidate 3 things you need to build really good applications. One is transactions. Now, I hope I don't have to explain to this audience what a transaction is and why a transaction is interesting. But I will anyway, right? Transaction, you call begin, you do a bunch of stuff. You read some data, you make some decisions, you write some data, and then you call commit, and it happens all at once or not at all. That's the A in ACID, and it's the I in ACID, etc. too. But it's the point of a transaction is that when I'm writing some code to add a new user to the system, and I have to go add a project for that user, and I have to go set its quota, and I have to look up here and decrement the available count and change their billing, I don't have to reason about what happens at every step of that code if someone else intercedes and changes the data underneath me, right? This is basic stuff. This is thread-safe programming, right? Transactions, so important, right? But again, I guess this is a hot take. I don't know why it is, right? SQL is not an expressive language, right? Almost no one writes their business language in SQL because you can't have an if statement in SQL. You can't run code, arbitrary code in SQL. You could use PL SQL, like stored procedures. No one wants to do that. Typically, you write stuff like this. This is just some Python ORM code that runs in a transaction, and it reads something from the database, and it checks an if statement, and it raises an exception and does a conditional check. This is how people have built database code for the past 50 years. Cool. So I don't have a problem with the old way of doing things, really. This is how like every big web service you use looks, right? You have your client on the web browser. You have a RPC server running code that looks like that Python code. It talks to a database that runs transactions. But there are some challenges here. There's two big glaring challenges. One is the obvious one for syncconf. There's no sync here. You have to keep polling the server and updating your data on the client. That's actually very hard for application developers. The second one, which you might not think about unless you've worked at a big company, right, is the API servers written by the API team. And they're like grumpy people, and you got to ask them to do stuff for you. And this is not a little point. This is a real issue because the world is now owned by the application developer. An application developer wants to write their code in their front-end language in TypeScript and have it in their monorepo, right? And so there's another option out there, which is quite popular, especially in platforms like Firebase or Superbase, etc., right? Where you put the client business logic on the client. You're like, hey, our target market is front-end developers. Put your business logic on the client. Send SQL statements to the server. There's a few issues here. One, you have to have this complicated row-level security rules to lock down your state so you don't leak it. The other one, the big one for me, is you're giving up on transactions. Probably. Because you can't easily issue a transaction from a client to a server. You can't let your phone or laptop call begin transaction on google.com, right? And then I go away and I've locked up a bunch of server resources. So this is kind of given up on transactions. So I think the kernel, the new abstraction for application development probably looks like TypeScript stored procedures running on a server and reactivity to solve the sync problem. So I like the old school model, but I think we should kind of amend it a little bit. So instead of having the API team write the API services in ways that are kind of unsafe, so a different team writes it, let's just have people write TypeScript stored procedures written in TypeScript using the same code as your front end. They got automatically sync to the server, run safely in a sandbox, and that runs transactions. And let's add a sync protocol on the client to automatically keep the client up to date with respect to data on the server. So how it looks in practice, you've seen this. I've been reusing this example for several years, so I apologize for this, right? But this is a really simple shopping cart example. And you have two major components here. On the left, we have items in stock, and on the right, we have my private shopping cart. And the left is shared. So if you were on this website and I was adding things to my cart, you would see this stock available for purchase go down automatically, and I would see it add to my cart. And this is a simple application. It's actually very hard to implement in a traditional way because of all the weird and interesting relationships between all the components and all the operations you might do. You've got to think about what happened with this cart and that user, and what happens if someone changes it while I'm adding it over here, right? In Convex, if we have these primitives, things are very easy. So this is the code, the actual code, for fetching the data on the left side of the screen. This just says, query all the items where there's remaining stock and return them. It runs as a transaction. That's not a very interesting transaction. Here's the transaction to add an item to my cart. This needs to be a transaction, right? This checks if above the screen, it checks if I'm authorized to do what I want to do. And then it checks if the item still exists. And then it throws an exception if there's no stock left. And then it adds an item to my cart, and then it decrements the available stock, right? It's a mutation, but all it does is reason about moving an item from the items table to my cart. That's all it does. It doesn't think about any race conditions. It looks like this. So how do we bind this to the client? How do we make the client update? Like polling and consistency are hard problems, right? This is the real code. This is on the client now. This is the real code for rendering the items component on the left. It says take the get items query, bind it using a React hook to the items component, to the items value, and then just render a div. That's it. And because it's React but for the backend, anytime data on the server changes, it automatically re-renders the client in a consistent way. Right? So this, to me, is transactional sync. This is the primitive we want to provide. So what do we need? I'll get into some details now. What do we need to build transactional sync? We need a runtime to run your code. We need a database, a commit protocol. And then we need to solve some of the traditionally hardest problems in computer science, right? Consistent caching and end-to-end consistency. So the Convex runtime has queries and has mutations. Queries are read-only, mutations change data. They're arbitrary TypeScript. We make sure they're side effect free and deterministic by remapping random and time, etc. And they can call into the database. So conceptually, it looks like this. You have the database inside of which you have V8 running isolates, and your code runs inside the database. You can just write regular code calling regular functions that can be thousands of lines long. You can call other functions, but it runs transactionally inside the database. In practice, it looks like this. Actually, in practice, it looks like this. I don't know, if there's time, we can talk about this or have other talks about how it all fits together. So I want to talk about how you build this thing. And I'll talk about it really fast. How would you build a transaction protocol that looks like this? And why is Convex a database and not just a sync protocol? So at the bottom of the stack, in this diagram here, if you can see up the top right here, there's Aurora or Planet Scale. It's a versioned write-ahead log with some convenient indexes, right? And then we have this service here called FunRun. Fun runs the function runner. All the cheesy names are mostly my fault. And function runner runs user code, right? So when you kick off a transaction and it says, hey, move that item from the items table to the cart, etc. It reads a snapshot of data from the database, and it's designed with indexes so you can efficiently read as of timestamp t, give me a consistent snapshot of the database. Then we run the code on that state as of the snapshot. And while we're running that code, we keep track of all the data ranges that query touches. So it reads a bunch of items, and maybe reads some user state, and it reads some cart state. And we know all the data ranges that have been read. We buffer up all the writes, and at the end, if no other transaction has their writes interfering with any of our reads, we commit the transaction. Otherwise, we retry it. There's more detail here. I'm going to skip over that. This is classic multi-version concurrency control. This is not like a crazy thing we've invented. This is a traditional way of building optimistic concurrency controlled databases. Our protocol is a little bit similar to, say, Foundation DB, for example. But there's some really key observations here. One observation is that for every query that we run, we know the input ranges that query depended on. And we also know the outputs to that query are a deterministic function of the code that we ran and those inputs. So we just pause and think about that for a second. Like, what can we do with those guarantees? What can we do with those features, right? We can do some really interesting things with those features, right? One is that caching comes for free, right? Sometimes people ask, how do I cache things in Convex? I'm like, you don't. We'll just do it for you, right? We have a consistent query cache. Server-side query cache. There's other functionality for client-side caches I won't talk about today. We know whenever the result of a query changes. Of course, we know all the writes that are happening in the system. So we know the results of this query that depend on the inputs are valid until those inputs change. Right? So we just cache it for you forever until those results change. Right? It's a query cache. A query cache is a much more powerful thing than a row cache, in my opinion. Row caches cache the data that gets written from the database. A query cache caches the result of a transaction. It saves you running all this work again. So a very large fraction of the work in Convex is just served out of a query cache. It saves us a lot of money, and it saves the user a lot of latency. The caching is hard. This is what I cared really deeply about architectural simplicity and composable abstractions, things that fit together well. And you know when an abstraction is not composable, when emergent complexity starts arising. Caching is hard. I'll give you an example of why caching could be very difficult. When you cache the results of a query, that's predicated on the source code for that query. And if I go and upload a new version of my mutation, that needs to invalidate the query. And if you write your code such that you keep manually adding all these corner cases and invalidating stuff, right, you end up with a very complicated protocol. In Convex, we just store the source code in the database, conceptually at least, right? And so the source code's in the read set for the query, right? So if you go and upload new source code, that just conflicts with the query and we reinvalidate and rerun it, right? Great. Reactivity comes for free. So if you have caching, and you know what the clients are watching on their screen, you can just send them the new value whenever it changes, right? So we have automatic end-to-end reactivity, right? And this, in my parlance, at least in the vocabulary we use, the Dropbox, is a sync protocol. It's very similar to what we, how this file sync protocol works, right? You have a WebSocket from the client connected to the server. The server knows all the use query hooks that are sitting on the client. It knows all the data you care about. And it can update that data and send it to you over the WebSocket to re-render your UI whenever the server state changes. So that's how we can do this thing here, this use query thing. This could be calling a relatively complicated query. And we say, hey, anytime the data changes, just re-render this component. And that's making this app re-render. Right? There's no polling here. The component on the left doesn't know that the component on the right exists. Right? It's just independent components showing a consistent state of the world. Now, this is actually true end-to-end consistency. Now, one thing that happens in a lot of applications is you have a lot of different engineers writing a lot of different functionality, and they don't want to think about what everyone else is doing, right? So there's only two components on this screen. If you go to like facebook.com, there's 1 bajillion components on that screen, right? And what's very undesirable is if an item shows up in my cart, but it's still available for purchase, right? Or it's very undesirable if I join Slack and I can send a message, but I'm not available on the user pane. Or I add a task to a to-do app, and the task shows up before the project that the task is in shows up, right? Because that's when you start adding all this very complicated logic on the client to track these dependencies. And the whole point of this is to make race conditions go away, right? Well, in Convex, we just know what you're subscribed to, right? So we just make sure that the client's always seeing a consistent snapshot of server state. The mutations go up over the WebSocket protocol with timestamps. The updates come down over the WebSocket protocol. And you will only ever see a state of the world that's consistent with some data on the server. So this is what I think the modern building blocks of app development are. Now, I hope we're right. I think we're right. I hope we're right. But I do very strongly believe that someone is going to come along with a new abstraction for application development. I think application developers are hungry for something better than just a glorified AWS, right? We need a higher level primitive that makes systems problems go away. And I think the biggest systems problem is distributed data sync. Someone's going to do it. And I think, and the Convex pitch, is that the two primitives we need are TypeScript stored procedures, lets you run transactions, it's written in the same language that your client is written in probably, and it's expressive. and also end-to-end reactivity, so you don't have to deal with all that polling logic and reasoning about interactions between different components on the screen. And that's it.